Thanks for this opportunity. It's a pleasure to be in Sheffield. In fact, I've been here before, a long time ago. My first course on extremes was taught by Clive Anderson, and it was a real pleasure to do that, and now I'm still doing that, so I'm really happy to be back here. Here my talk is going to be about extremes and climate, but first I would like to acknowledge my two colleagues, Armel, Guillou, and Theorich, who are from University of Strasbourg. So basically, the question I would like to answer is very simple. So suppose I give you like temperatures, okay, daily temperatures, max of daily temperatures here in Sheffield, and you just want to answer the following question. If you look at the last 30 years of extreme temperature in Sheffield, are they different from, let's say, from 1900 to 1930? Okay, so that's the basic framework of my talk. Okay, and to do that, I need to cover basically three different topics. One is about climate, and it's about the entropy, and maybe people are less familiar with that, so I'm going to spend a little bit on that. And the last part is to connect the three by fitting the extreme value theory. Okay, so that's basically the outline. And let's start with the climate here. And I suppose like everyone knows that the Earth is warming. And so here what we like to do is not basically to say, well, we know it's warming in the mean, so obviously in the extreme it's going to warm because there's going to be a shift. We would like to do something else. We like to say, if we remove the trend, the mean average warming, is it possible to get an idea about how extreme change in terms of temperatures? I'm not going to speak about the topic of attribution. I'm not going to try to answer why is warming. Some people have done that. It's called detection attribution. And for example, Richard Smith have worked on that, and Francis Wyers and others. So here I don't want to work on that. I'm just going to work on the detection problem. Two time series, are they different or not in terms of extremes? Here just a reminder that it's getting hot. Here it's the latest report of the IPCC, and here it starts basically 1850 and go to 2013, and you can see it's warming. I don't know if there's a pointer or not, but maybe I can use a mouse. It's okay. Okay. Thanks. So you can see it's warming. Here we are kind of a plateau right now, and you have the bumps here. It's kind of a, you can see this is a decadal mean. Okay, in the 70s it was cooler. Here at the beginning of century was a little also there's a dip, and after it's like that. Okay, so basically that's the global picture. Okay, if you average over the Earth. If you look at a different country, a country like France, because here you can see 1880, 2000, and so you have a bumps here in the 70s again. In the 30s, we have also little bumps. And here is the same kind of picture for the northern hemisphere and southern hemisphere. So we have the global trend. Okay, so obviously the extreme temperature are going to be warmer here. Okay, so what I would like to know is, after removing this trend, is it still possible to find a difference in terms of extreme? Because they could have shifted in terms of variance or in terms of the intensity after removing the trend. To become a little more precise in terms of my data, I randomly chosen a place, Paris, and I took the station Montsouris, okay? And why? There's different reasons for that, but one of the good reasons is temperature has been measured at least from 1900 to 2010, and basically they represent 40,000 daily maxima of temperature. Okay, so a lot of data. You can imagine there is an urban island effect, but I don't think it's the case, because Paris is an old city. There's been always people near Montsouris. So now what I'm going to So I take this time series of 30,000 points. I'm going to do that for each season. I'm going to remove the trend, okay? And then after, I'm going to take the 95 threshold quantile, and then I'm going to look at the time series again. So this is the trend I'm going to remove, and so you can see, again, in the 70s, there's a dip. In the 30s, there's like a bump. But basically, it's, which is kind of surprising, because at the local level, it's like at the regional level and the global level. And so after removing the trend and looking at the 95 percentile quantile, I get this data set. Okay? And so the question is this extreme here, let's say the last 30 years, are different than here or here? Okay? I'm going also to look at other points, and I don't want to say Europe because here, over Europe, because England here is not here. I suppose the UK is still part of Europe. But why I took these stations is because they are freely available. You can look at the European Climate Assessment data set, and you have all the cities here, none from the UK. But what's very interesting for us is this column here, the first year, 1876, 1894, 1874, and so on. So I pick up the longest time series. Because if you want to speak about extremes, you need to have a long time series. Otherwise, it doesn't really make sense. Like when people look at extreme for like the last 20 years or 30 years, I don't think it's very reasonable for many different reasons. So, of course, I'm not going to speak about the quality of the data here, maybe in the discussion. So here, 30 years, 8 years, and then I want to compare. So I'm not the first one to look at this question, and there is a lot of different ways of doing that. One classical way is basically to use extreme value theory in the univariate case, let's say, and say, if you look at excesses above a threshold, usually a good fit is a generalized Pareto distribution. That's what the theory tells us. And if you look at block maxima, you can use a generalized extreme value distribution. So that's fine. But the problem with this approach is like you have usually 2 or 3 parameters. So you can have one change in one parameter and change the other parameter, and so on and so forth. And then you impose a specific density, which is not maybe the right one, because extreme value theory tells you it's when the sample size is large and the threshold is large. Okay? So, but there is some very nice work about this kind of thing, about temperature, like this paper here. So what we would like to do is something a little bit different. We don't want to impose a generalized Pareto distribution or generalized extreme value distribution. So we don't want to impose a parametric family. We want something very fast. Why? Because here I'm going to apply that to, let's say, 30 stations. But if I want to apply that to climate models, maybe I will have 10,000 points or 100,000 points time series. So I want to go something very fast. Of course, we like to have good statistical properties, something we can interpret. And one key point, at least for me, I work in a climate lab. And I like when people use a tool I develop in terms of statistics. And if I speak with them about the general extreme value distribution, the GPD and stuff like that, they can do it, but it's not that easy. But if I speak about other statistical tools, like taking a mean or computing the entropy, they are more likely to like that. So our assumptions here are, I suppose the trends and annual cycle has been removed. If they are not been removed, it's not a big deal, because it's easy to detect a change. So suppose after removing the annual cycle and the trend, we are basically in this framework. So we don't assume that I'm going to compare 2 different time series. We don't assume that 2 time series have the same shape parameter in terms of extreme value. So it could be anything, basically. So now let's go to the second part of my talk, entropy. Okay, and entropy, why we like that? Well, because it's something used in many different fields. And when I speak with climatologists, they like statistical physics, and they understand entropy, basically, an order, a measure of disorder. And also, if you think about computer science, they like also to use entropy. So the entropy is simply the log ratio of 2 the density, and here you have F, the PDF of X, and G is the other coordinate. Okay, so in my notation, they are going to be very simple, but I don't have a blackboard, so I'm going to say it orally. So X, the random variable X, at the PDF F, okay, and the random variable Y at the PDF G, okay. So, and so you compute the ratio, and if this is small, then the F and G are close to each other, okay, and you can make something symmetric by flipping F and G. Okay, so that's a classical definition of the entropy. And also what is nice is like if we could compute that for extremes, you can make the link with selection criteria like the AIC, BIC, and something like that. If you like to make the link also with scoring rules using in forecast, it's possible to do that. And also it's just one number. So that's very easy to give to people in climatology. So the problem with that, it's the following one. It's to compute that, I need to know F and G. But remember, I don't want to impose F and G. Okay, so that's an issue. And so how to solve this issue? So let's go back to, no, not let's go back. Let's try to visit a little bit extreme value theory here. And usually I like to put this picture here, especially after lunch, because people are more likely to listen because they see a naked man. But what I want to say here is the always. This is a picture taken from a community in Ascona in Switzerland. In fact, we co-organized that with Jonathan Tan and Anthony Davidson a few years ago. And here is the modern life. So what I mean by that, if you think about likelihood and PDF, people love the PDF. Like the PDF for the Gaussian distribution is fine. But if you look at extreme value distribution, people don't like to use with the PDF. In fact, what they like to work with, it's a CDF. And not the CDF, it's 1 minus the CDF, the survival function. What you are interested in when you do extreme value is not f of x, it's a probability of x greater than x. That's the object of interest. And in fact, it's much easier to define in extremes. So this is a key idea of my talk. If you understand that, we are basically done, which is good. So that's written here. But the problem here, you can see I have f, the PDF, but I would like 1 minus f, the survival function. Okay? I have a density. And g is the same. I would like to have 1 minus g, the survival function, instead of small g. So what we are going to do is just replace that. F by 1 minus f, and g by 1 minus g. So let's do it. Before doing that, we are interested in extremes, so at some point we need to introduce a threshold. So before, when I defined the entropy, it was true for any x. But here I'm going to just look at x given that x is greater than u. So it's a conditional random variable, and the density is just the ratio f of x divided by f bar of u, the survival function. So what I would like to compute is this now. For any given u, I would like to compute this. Okay, so it's just the entropy for the survival, the conditional variable. So this is the main result of the paper in some sense. It just said that. It just said what I said before. Here we have f of u, but we don't want a density. So if we replace that by g bar, and here you have g bar of u and g bar of u here, this quantity here is basically the same as this one for u large. Okay? So it's at the first sight, it's pretty maybe surprising, but it works basically because if you look at extreme value theory, most of the law you have is kind of power laws. And so the density and the survival function are very close to each other. But basically, this is the main result of this paper here. So if you have to compute the entropy like this, then you can use this approximation here. Okay? Let's see if it works in practice. We know it will work when U gets large. It's possible to prove that. But here what I did is I did a little graph where you have U, here's a threshold on the x-axis, and here you have the relative error because the true entropy is, in this case, for the generalized Pareto distribution, and the approximation I've just showed. Okay? And so when you can see that for U large, the approximation is getting better and better, it's closer and closer to 0. So basically, and this is true for any kind of shape parameter. So the shape parameter, sorry, maybe I was not clear about what is a shape parameter. When you work with a GPD, a generalized Pareto distribution, you have the most important parameter is called the shape parameter, and it drives basically the decrease of the tail. Okay, so if the shape parameter is positive, that's called a heavy tail distribution. And if the shape parameter is negative, that we have a bounded tail. So in any cases anyway, the approximation shows that for U large, you can approximate this one by this one. Okay? Now we have to think in terms of inference. Okay? How to compute this? Well, this is fairly easy to compute because now we don't have a density anymore, but we have a survival function. So what you can do, you can just plug in the empirical survival function. Okay? So what you have a non-empirical estimator of this quantity, and this is very fast to compute. Okay? If I give you 1 million, n equals 1 million, you can still compute that very quickly. Okay, so you don't have to do any estimation, you don't maximize or likelihood or anything like that. You just plug in this. In fact, this is a rank of the data with respect to G or to X, basically. Okay. What's happened under the null hypothesis? If the two distribution have the same survival function. So coming back to what I said at the beginning, if you look at Sheffield, you look at extreme temperature above a certain threshold, that's F for the last 30 years, and you take a different time period, let's call G, and then you say, oh, they are the same. So in this case, if they are the same under the null distribution, then of course the empirical distribution in distribution will be the same. And it means that these statistics under the null distribution is distribution free. It doesn't depend on the F. Okay, so I think for people doing extreme value theory, it's kind of common that this is basically a uniform distribution. But for people not used to extreme value theory, it means like it's just a rank. So under the null hypothesis, if you take a uniform, an exponential, a Pareto, a Gaussian distribution, it's going to be the same number here. So which is nice because you just have to you have to compute that once, and that's it. Then you can test. I mean, you can compute your p-value from that. So now I'm going to show you some example about the inference, okay, and see how it works. So I'm going to have a few tables, and what are going to be the table? Tables are going to be filled with numbers, and the main number is going to be the number of false positives, so wrongly rejecting that F equals G, and negative, false negative. So I'm going to do, each time I do 1,000 replica, and for different sample size, okay? And because I need, for my simulation, I need to fix a PDF, And I'm going to take the generalized Pareto distribution as examples with different shape parameters. Okay? So let's see what that means in practice. So here, suppose in Sheffield, let's say the shape parameter of the GPD, if it is the case, is minus 0.1. Okay? And suppose you take 10,000 observations for one period and 10,000 observations for a different period. What's going to happen? Because you repeat the experiment 1,000 times, so and you have a 95 confidence level, so that means you are going to have 50 false positive, and what you expect is to have 0 otherwise. Okay? Of course, when you have a small sample size, you get different result. Here you should have 0, but because the sample size is small, you get something. You cannot make the difference between minus 0.1 and minus 0.2 if the two time periods have different extremes. Okay? You could say, well, what's happened if I use Kolmogorov-Smirnov, for example, the classical one that people use at least in climatology a lot. You could say, well, it works fairly well, Kolmogorov-Smirnov. For example, for n equals 100, here our method gets 3 out of 1,000. Here I get 42, so it's worse, but not that. I mean, we improve a little bit, okay, but not that much. So the big difference is because the Weibull distribution is bounded. So Kolmogorov-Smirnov is fairly okay for that. But now if I look at Frechet it's Evitel, okay, which means that you can have large value and sometimes you can have very large value, okay? So here, like this is, suppose the shape parameter is 0.1. For example, this corresponds basically to light precipitation, basically. And so the truth is 0.1, and if the shape parameter of G, the other distribution, is also 0.1, then you should get 50. So if you look at Kolmogorov-Smirnov, you don't get 50. With our method, you will get closer to 50 here, false positive. And then what's very surprising, at least, is even with 10,000, so if your sample size is 10,000, you should get 0 here, and that's Kolmogorov tell you 648. So it's really a huge mistake. Here we should get 0, but we get 9, which is out of 1,000. It's not that bad. But even with our method, even with 1,000, is not that good either. It means, which I think is fairly well known in extremes, it's like if you have positive shape parameters, it's very difficult to make the distinction between two distributions. And people should be very careful if they know they have a positive shape parameter. They need a really big sample size to make any statement. So here you can do other simulation, like you can do Gumball-Weibull or Gumball-Frechet, but basically, in all cases, for example, here, I'm using that because temperatures, extreme temperatures, are usually type of either Weibull or Gumball, most of the time. So either bounded or Weibull. So if I have Weibull kind of distribution, then you can see with 500 or even 200 observation, I get fairly good result to make the distinction between 0 and minus 0.4 or even minus 0.3. So if I have a few hundred points, I can make a few statements. So now, let's go back to Paris and see how it works in practice. So what I'm going to do, as I said, I'm going to take two different time periods, like this one, it's 30 years, because climatology usually is 30 years. So I'm going to take two climatology. I'm going to compute the statistic I propose. Then we are going to compute the p-value, and then we are going to say the two time series have different extremes or not. And I'm going to do that for different time periods by sliding a window. Like that, I can have a picture in time. And then I'm good. So here, you have 4 different panels, because we have 4 different seasons. At the top, it's the spring, summer, winter, and fall. Here it's basically 1920, 2000, the x-axis. And you can see, like, let's start with the summer. The summer, it looks like in Paris, after removing the trend, okay? If I compare the extreme, the dotted line here is the p-value of the statistic. So if you are under it, that means you are fine, there is no difference. If you are above it, that means you reject the null hypothesis. So the summer looks like nothing is changing. It looks like the extremes in the summer in Paris didn't change the summer. In the spring, it's very different, and in the fall too, okay? So if I look at the fall in particular, I can go back to the picture, to the real data. And that's what you get. So you can say, well, we don't need a test here to see that the extremes here are different than here. But, of course, I didn't see the data first. So the point is, if I have to do that for hundreds of thousands of stations, I could do that quickly and detect this kind of thing. Now, if I go back to the, not Europe, but a small part of Europe, here you can see the black points are my stations, and the circle here means how far, how many years are reject the hypothesis, the null hypothesis. So the bigger the circle is, that means the more likely that there is a difference in the extremes. So during the summer, this was Paris, it was not a big change, and most of the station is like that. But if you look at the fall or the spring, even the winter in the north, it looks like there's been difference. So beyond the mean, it looks like if there is a change in the extremes for the maxima. You could do the same exercise for the minima, of course. You have just to multiply by -1, and you get also different patterns, which means that the extreme temperature looks like changing in space. So now I'm going to sum up a little bit what I want to say here. So what I try to show you basically here is to give kind of a link, a connection between extreme value theory and the Kullback-Leibler divergence, okay? What we try to do is to propose a simple non-parametric estimator of the Kullback-Leibler divergence for excesses above a threshold, and it's non-parametric, so we don't need to assume an explicit density. Also, it's very fast. We compare with different tests. They don't work very well, but the Anderson-Darling test, it's a good one. It basically gives the same time of result that we have. Of course, there is a drawback here. It's not a real drawback, but this is just to answer one question, is to say, are the extreme different from different time periods? We cannot compute a return level, for example. Okay, that's a different story. Right now, in terms of climatology, it looks like over Europe, when I say Europe, it means like the region I defined before, it looks like significant changes in terms of extreme temperature, even after removing the trend. Right now, I'm working on the multivariate case, and also we are applying that to very large climate output models too. And I think I'm going to stop here. Thank you.
Thank you, Phillippe. I think we've got time for just a couple of questions, if anybody has questions. And again, can I ask you to use the microphone?
I was just wondering what distribution you used for the Kullback-Leibler divergence. Did you use chi-squared to decide, whether it was a large value or a small value?
Oh, yeah, it's a very important point. Here, I don't need to to compute under the null hypothesis, if I want to reject the null hypothesis,
Yes.
I need to compute these statistics,
Yes.
and it's distribution free. So,
Okay.
which means I just have to take a uniform distribution. For example, you give me a sample of n equals 100, and I could many times, and tabulate it for once, and that's it.
Okay. Thank you.
You have a question?
My question is, are you familiar with what Lawrence Leon has been doing in the last years? He has been looking at similar problems by using tail equivalence. So he looks at the ratio of the distribution like that moving table you have. And he estimates each of them by empirical distribution functions. His intention is not exactly to make a test of hypothesis, but to see trends in how things move. But I think he assumes equality in the shape parameter.
Yeah.
Phillippe, could you please just summarise the question for the microphone?
Sure. So the question was about the recent work by Laurence de Hahn, and he's working on a similar topic, and by moving a sliding window over time, let's say. And but I think what it does is, like as you say, he supposes there is the same shape parameter for both distributions, and in this case we don't have this restriction.